Hello everyone! Today I'm going to be talking about lessons 2 and 3 of chapter 22. First, we are going to be talking about unsaturated hydrocarbons. Before we dive into alkenes specifically, it's important to understand the difference between saturated and unsaturated organic compounds. A saturated compound is one where each carbon atom is bonded to the maximum possible number of hydrogen atoms. In other words, all the bonds between the carbon atoms are single bonds. On the other hand, unsaturated compounds have either double or triple bonds between some of their carbon atoms. These multiple bonds mean the compound holds fewer hydrogen atoms than the saturated one does. This is important because the type of bonding changes the structure and properties of the compound. Now, let's talk about alkenes, which are a type of unsaturated hydrocarbon. The term hydrocarbon simply means a molecule made up of only hydrogen and carbon atoms. What makes alkenes unique is that they contain at least one double bond between two carbon atoms. This double bond is a defining feature and significantly affects how the molecule behaves chemically. In chemical formulas, a double bond is usually shown as two parallel lines between carbon atoms. It's important to note that while alkenes must have at least one double bond, the rest of the bonds in the molecule could still be single carbon-carbon bonds or carbon-hydrogen bonds. A common and simple example of an alkene is ethene, which is also known as ethylene. Ethene is made up of just two carbon atoms and four hydrogen atoms, with a double bond between the two carbon atoms. Because it's the smallest and simplest alkene, ethene is often used to demonstrate the general structure of this group of compounds. It's also very important in the chemical industry as it is used to make plastics or more. It's also useful to compare alkenes to another group of hydrocarbons called alkynes. Like alkenes, alkynes are also unsaturated, but instead of a double bond, they contain at least one triple bond between two carbon atoms. In a chemical structure, this triple bond is shown as three parallel lines between two carbon atoms. The presence of a triple bond in alkynes makes them even more reactive than alkenes and changes their chemical behavior. So, let's recap what we learned. Saturated compounds have only single bonds and hold as many hydrogen atoms as possible. Unsaturated compounds, like alkenes and alkynes, have double or triple bonds. Alkenes are hydrocarbons with at least one carbon-to-carbon double bond. Their structure is often shown with two lines between carbon atoms in chemical formulas. Ethene is the simplest alkene. Alkynes, on the other hand, have at least one carbon-to-carbon triple bond. And that is the end of lesson 2. Next, we're going to be talking about chapter 22.3, which is about isomers. Now that we understand the structural characteristics of alkenes, especially the importance of double bonds and how they affect the molecule structure, next, we're going to be talking about another important concept in organic chemistry, isomerism. This topic is directly related to what we just learned because the way atoms are arranged in molecules, especially those with double or triple bonds, can change the compound's properties even when the actual chemical formula stays the same. So, what are isomers? Let's start with the basic definition. Isomers are compounds that have the same molecular formula, meaning they contain the same types and numbers of atoms, but they're arranged differently. Think of it as building with the same set of Lego bricks. You can build different shapes using the exact same pieces just by putting them together in different ways. That's what happens with isomers too. The first type of isomer we'll look at is called constitutional isomer. These are molecules that have the same chemical formula, but the atoms are connected differently. Because of this difference in connectivity, constitutional isomers can have very different physical properties like boiling points and melting points. That's because the structure of a molecule influences how it interacts with other molecules, how tightly they pack, how easily they evaporate, and so on. The second major type of isomer is a bit more subtle.
These are called stereoisomers. In stereoisomers, the atoms are connected in the same order, just like in a constitutional isomer, but the difference is in the three-dimensional arrangement of those atoms in space. Even though the bonding pattern is the same, a small shift in spatial orientation can lead to entirely different properties of behaviors, especially in biological systems. There are two main categories of stereoisomers, which include cis-trans isomers and enantiomers. Let's begin with cis-trans isomers, also called geometric isomers. These usually arise in compounds with double bonds, like alkenes, which we just talked about. Because a double bond is rigid and doesn't allow atoms to rotate freely around it, the position of atoms on either side of the bond matters. In a cis configuration, the same atoms or groups are on the same side on the double bond. In a trans configuration, however, they are on opposite sides. Even though the formula and the connections are the same, the orientation changes how the molecule behaves. For example, cis isomers often have higher boiling points because the shape of the molecule allows for stronger intermolecular forces. The second category comes into play when you have a carbon atom bonded to 4 different atoms or groups. This carbon is called asymmetric carbon or chiral center. This special arrangement allows for mirror image isomers called enantiomers, also known as optical isomers. Here's how to think about it. Hold up your left and right hands. They're mirror images of each other, right? But no matter how you rotate them, you can't superimpose one exactly onto the other. That's the same idea with enantiomers. They are non-superimposable mirror images of each other. Enantiomers have identical physical properties such as boiling points, melting points, and densities. But what makes them fascinating is how they behave differently in biological systems. Many biological molecules, like enzymes and receptors, are chiral themselves, meaning they can tell the difference between enantiomers. One enantiomer of a drug might be effective, while its mirror image could be inactive or even harmful. So to sum it up, isomers have the same molecular formula but different structures. Constitutional isomers differ in the order in which atoms are bonded. Stereoisomers have the same bonding order but differ in spatial arrangement. Cis-trans isomers result from limited rotation around double bonds. Enantiomers are mirror image molecules around an asymmetric carbon. Thank you for your attention.